So what we learned so far? We start talking about different types of variables. We said that, well, a variable can be discrete. What's the meaning of discrete variable? It means that it is countable. Countable variables. Like the number of residents in different properties. So example, the number of residents in each property. Another example, the number of students sitting in this class. The number of students in this class. These are all examples of countable or discrete variables. What we learned about discrete variables is that, hey, we can use a histogram to graph and visualize the data related to discrete random variable. So remember that here we had x on the horizontal axis, and on the vertical axis we have the relative frequency. Our relative frequency is f divided by n. Then we get some bars. These bars help us to visualize the distribution, the behavior of this probability distribution. So this is our probability distribution. Then what else we learned? We learned that, well, based on the question, we can find different probabilities. For example, if we have x equals to 1, x equals to 2, 3, 4, 5, 6, 7, 8, we can find the probability that x is less than 4. We can find the probability that x is less than or equal to 4. We can find the probability that x is exactly 4. We can find the probability that x is larger than 4. And also we can find the probability that x is larger than or equal to 4. Based on the question, we can find each of these probabilities. If it says, hey, x is less than 4, it means that x can be 3, 2, or 1, and we're going to add the probabilities for these 3 bars. If it says, hey, x is less than or equal to 4, it means that x can be 4, x can be 3, x can be 2, x can be 1, and we're going to add all of these probabilities together to find the probability that x is less than equals to 4. If it says, hey, find the probability that x is exactly 4, it is equal to the probability, the height of this bar. If it says, hey, find the probability that x is larger than or greater than 4, it means that x can be 5, x can be 6, or 7, or 8. So for this case, x is larger than 4. We're going to add these probabilities together to find the probability that x is larger than 4. If it says, hey, probability that x is larger than or equal to 4, it means that in this case, we have to include 4 as well. We need to find the probability that x is 4 plus the probability that x is 5 plus the probability that x is 6 plus the probability x is 7 plus the probability that x is 8. One of the famous discrete probability distribution is called binomial distribution. So when you see binomial distribution, is one of the famous discrete variable probability distribution. Is a discrete probability distribution. To find the probability related to binomial distribution, we follow the exact same method and process. Well, now I expect you to ask, so you gave us examples about discrete or countable variables, the number of residents, the number of students. What if it's not countable? Well, I'm glad that you asked. If the variable is not discrete, we call it continuous variable. Continuous variable. For example, when you're talking about weight, height, it means that you're dealing with continuous variables. Weight, height, weight of student, height of students. When you're talking about volume, when you're talking about area, these are examples of continuous random variables. Well, how do we visualize the graph? The graph, it has very small bars. So when you're graphing a probability distribution for a continuous random variable, your vertical axis is not f over n. It follows p of x probability of x. In this case, you have very small bars. The bars are attached together and they are very, very small bars. Thin and small. So small that we don't care about bars anymore. We just follow the behavior of the height of the bars, and based on the shape, the distribution, which is usually we are interested in normal or bell-shaped graphs, we work with symmetrical bell-shaped graph. But in general, the behavior is like this. These bars are very close to each other, tiny bars, they are very thin, versus the bars that you saw here, the bars in continuous random variable, they are very close to each other. These are your bars, and this is the behavior of your graph. So see, the difference between these two graphs is that in discrete random variable, you can actually see your bars and you can find the probability by looking at the height of each bar. But when it comes to continuous random variable, these bars are very close to each other. These are very small, tiny little bars. We don't see the actual height. So what we do, we use a probability function to calculate these little heights. So when it comes to continuous random variables, we're interested in introducing something that we call z-scores. Very well. So let us start. Z-scores and normal distributions. Introduction. There are many populations in the world. For example, there are people of different nationalities who live in different places and do different kinds of work and who have different kinds of job experience. Sometimes we need to compare values from different populations. People often say you can't compare apples to oranges, but in statistics, we do it all the time. But how? The secret is in the standard deviation. Remember that standard deviation was one of the examples of variability, the measure of variability. Well, the standard deviation allows us to compare values between different populations. In previous lessons, we learned a lot about standard deviations. And remember that standard deviation gives us a measure of variability. On average, what's the difference between a data and the mean? We use the standard deviation to measure how far values are from their mean. So this is the use of standard deviation. Again, remember that for measure of variability, we used range, which was maximum minus the minimum. In maximum minus the minimum, we only took on the maximum value and the minimum value in our collection, which wasn't very useful. So we turned on to standard deviation. Standard deviation of a sample was denoted by S of X. And standard deviation of population is denoted by sigma. So sigma or standard deviation of population, S of X was standard deviation of sample. So when you see different questions and they don't mention anything about standard deviation of population or standard deviation of sample, but they give you S of X or just S equals to a number, you quickly say, hey, this question is talking about a sample. Sometimes they give you sigma. This little sigma is different from this big sigma that we use for summation. This capital sigma, Greek letter capital sigma, it means we have sum or addition. This small sigma means that we have the standard deviation of population. So symbolically, we use S of X to represent the standard deviation of sample, and we use sigma, this little sigma, to show that we have the standard deviation of population. Let's try these. A company has a job opening for a high-paying and important position. Well, okay, it's only hiring one person for this position. One person. Your team will recommend the candidate who will get the job. After much work, your team narrowed this choice down to 2 outstanding candidates. Both job candidates are well regarded and equally qualified. Okay, well, it makes it a little bit hard for us then. The last step of the hiring process is a personality test. The job is going to be very stressful, and the company believes that the personality test will reveal whether a candidate can handle stress or not. Both candidates have the results of such a personality test in their file. Unfortunately, they didn't take the same test. Using the following results, whom do you recommend for the position? Be prepared to justify your choice to the company chief executive officer. Well, take a look at these information that we have. We have the first candidate, name of the test taken, stress sanity simulator, the mean. Okay, we are the statistician. The mean is 740. Standard deviation, variability is 30. The candidate score is 800. Okay, 800. So again, for this test, the mean is, the typical value is 740. It means that they ran this test before, throughout the years, and what they got is that a typical score for this test is 740. The variability is 30. It means that on average, a random test is 30 score away from the mean. The candidate got 800. This is your candidate A. So now let us take a look at candidate B. I'm going to use a different color for this. Name of the test taken is modeling mind management, a different test. The mean score of this test is 65. The standard deviation of this test is 10. And your candidate scored 95. Well, okay, so these are the information that we have. What are we going to do? How are we going to compare these two data together? This is the main question that gave rise to Z-score. What is Z-score, or standardized test statistic, is denoted by Z equals to X bar, the mean of the sample, X, minus the mean divided by sigma. So here you have the mean score. This is your population mean. Standard deviation of the population is given, and your candidate score is 800. So take a look at this. This is your mean of population. Remember that this is mu, the sound of a cat, mu, the mean of the population. Standard deviation of your population is denoted by sigma. And this candidate score is X value. Let us find Z-score for this candidate. So our Z is equal to X 800 minus the mean is 740 divided by sigma, which is 30. So z-score for the first candidate is going to be 60 divided by 30 or 2. This is the z-score for the first candidate. Z is 2. We convert everything X into Z because we want to compare these two candidates' score together. If they are written this way, it's going to be very hard for us to compare these two candidates together. Now for the second candidate. The z-score for the second candidate is, again, X, which is 95, minus the mean, which is 65, divided by sigma standard deviation, which is 10. So we get 30 divided by 10. Our z is 3. So the z-score for the second candidate is 3. So what is our conclusion here? Our conclusion is, since the z-score of candidate B is larger than the z-score of candidate A, it means that candidate B is a better candidate. So since the z-score of candidate A is less than the z-score of candidate B, it means that we are happy with our second candidate. Let's put a smiley face here, that we're going to recommend candidate B for this position. Okay, let's go over some more examples. Okay, perfect. Next steps. Standard deviations are used to measure how far values are from their mean. A sample standard deviation is denoted by S. Sometimes they use S sub X. So for sample standard deviation, you might see S or S sub X, especially when you're using your calculator. Calculator uses S sub X to represent sample standard deviation. Population standard deviation is denoted by sigma. So the difference between these two letters, S for sample, S for sample, and population standard deviation denoted by sigma. So remember that when we are talking about population parameters, we use Greek letters. The symbol known as sigma is the lowercase Greek equivalent of the English letter S. Okay, language tip. As we proceed, we use the following symbols frequently. Mu, population mean, sigma, population standard deviation. Okay, give us more examples. Well, let us take a look at question 2. It says, hey, a grocery store owner rates the quality of her oranges on a 0 to 20 scale. She has 15 oranges. So 15, n is equal to 15. N is 15, or this is your sample size. With ratings listed below, okay, for each of the oranges, she rated these oranges. Well, for this problem, we will think of the 15 oranges as an entire population. So since the question is saying that, hey, we're going to use population, it means that we only have n equals to 15, and this sample is equal to the population. So you might say, hey, I'm going to change this to population size, which is absolutely fine. So as you read the question, the example, you need to make necessary changes. Population size. Okay, let's see, what do we have? The population mean rating is 10, mu is equal to 10, and the population standard deviation is 4. What does the standard deviation tell us about variability with respect to the population mean? Okay, it's not very hard to answer this question because we know the definition of standard deviation. It tells us that the average, so it tells us that the average of the distance from the mean, which is 10, is 4. The mean is 4. Suppose you buy the orange with a rating of 14. Is this above or below average in quality? So remember that the average quality is 10. Average quality is 10. The rating for the orange you're purchasing is 14. So obviously 14 is larger than 10. So we expect to have a better quality for that orange. So you can answer, since 14 is larger than 10, so it is above the average. Remember that the average is 10. Now question says, how far does this value deviate from the mean? What's the difference between this value and the mean? So obviously 14 minus 10 is equal to 4. So when it comes to data like this, these are your X values. We use a horizontal line and we assume that the population is normally distributed. The population is normally distributed. When the population is bell-shaped or normal distributed, the mean of the data, the typical value, the center is a number in the middle of the horizontal line. This is your mean. If you're working with population, you denote it by mu. if you are using a sample, you're going to use X bar. You can divide this line using standard deviation. Mean plus 1 standard deviation, mean minus 1 standard deviation. So you are moving 1 unit to the right, 1 unit to the left. What is that unit? That unit is sigma, or standard deviation. So again, the typical value is in the middle, 1 standard deviation above, 1 standard deviation below. We can continue this process. Mu plus 2 standard deviations. Mu plus 2 standard deviations, and mu minus 2 standard deviations. So again, the typical value is here. We're just dividing up this horizontal line using the unit, which is standard deviation. And finally, the last division is using mean plus 3 standard deviation, mean minus 3 standard deviation. The difference between each of these is 1 standard deviation. So 1 sigma, 1 sigma, 1 sigma, 1 sigma, 1 sigma, 1 sigma. For example, for this example here, oranges, the mean of the population is just 10. We assume that this population is normally distributed. Normally distributed, normal distribution, bell-shaped graph. The typical value, the mean is in the middle. The mean is given to us as 10. So we know that mean is 10, the typical value, 10. What is the standard deviation? Standard deviation is 4. So by using the mean and standard deviation, I can divide this guy up by 4 units. 4 units, which is my standard deviation. 10 plus 4, 14. 10 minus 4, 6. 14 plus 4, 18. 6 minus 4 is 2. 18 plus 4, 22. And 2 minus 4 is -2. We don't have negative ratings for the oranges. So it means that if you see a rating less than 2, it means that that orange is not qualified to be in this rating at all. So again, this is my mean, typical value. Values above 10 count as oranges with high quality, like 18, like 14, like 16. All oranges on the right-hand side, ratings, they are high quality oranges, and the ones that have below 10, they are low quality oranges. This is our normal distribution graph, and these are the data X values on the horizontal axis. Perfect. So we have our information here. Okay, I'm going to just leave this guy here. So this says, we're moving on to the next question. So in C, the question was, how far does this value deviate from the mean? It was 4. And then part D says, how many standard deviation is this? We know that 4 is just one standard deviation. So this is one standard deviation. So take a look at the question again. So in previous question, they picked one orange with rating equals to 14. And we know that it's above the average. And how far? What's the distance? The distance is 4. But what's the relation between that distance and standard deviation? Take a look at your graph. This is one standard deviation above the mean, just one standard deviation. So one standard deviation above the mean. Next question, it says, well, the number of standard deviations that a value is from the mean is called the z-score. We know that z-score is equal to x minus mean divided by sigma. So let's calculate that. It says, what is the z-score of orange with a rating of 14? X is equal to 14. So we have z equals to 14 minus, what is mean? We know mean is 10. What is the standard deviation? Standard deviation is 4. 4 divided by 4 is 1. So z-score is 1. F says, okay, what is the z-score of an orange whose rating is 18? Formula for z-score is x minus mean divided by sigma. So my z is now 18. X is 18. 18 minus mean. Mean is 10 divided by sigma, which is 4. So we have 8 divided by 4, which is 2. So z-score is equal to 2. So obviously, since 18 is larger than 14, you say that, hey, the quality of the orange with 18 as rating is higher than the quality of the orange with 14 as its rating. But if we don't have these original data and we only have z-score, since 2 is larger than 1, we say that the quality of the second orange is higher than the quality of the first orange. G says, we have stated before that the deviation of a value like x from the mean is x minus mean. The z-score of x is the number of standard deviations from x to the mean. So we know that the formula for z is x minus mean divided by sigma. Change this line divided by sigma. This is an important formula. We need to know our z. As a statistician, we're going to use this formula a lot. X minus mean divided by sigma. Use your formula to determine the z-score of an orange with a rating of 4. So rating is 4. What is this? Is this X? Is this mean? Is this sigma? Well, I know in the question, my mean is given. Mean or typical value is 10. Standard deviation is also given. It is 4. So what I'm left with, X is 4. So X is 4. Mean is given as 10. Sigma is given as 4 as well. So Z, the Z-score, X, 4, minus mean, 10, divided by sigma, which is 4 again. So what do I have here? I have negative 6 divided by 4, which is negative 1.5. My Z-score is a negative number. My Z is negative. That's absolutely fine. You might have positive or negative Z-scores. But what's the meaning of this negative Z-score? It means that this negative sign says, hey, this orange with rating of 4 is below the mean. The value is below the mean. Interpret the Z-score for the orange with a rating of 4. This orange with rating of 4 is 1.5 standard deviation below the mean. So this orange with negative 1.5 Z-score is 1.5 standard deviation below the mean. So this orange with Z-score negative 1.5 is 1.5 standard deviation below the mean. Use your formula to determine the Z-score of an orange with a rating of 10. So we are trying to compare different Z-scores for different oranges. Our X is 10. Mean is also 10. Sigma is 4. These information are given to us in the question. So my Z is X minus mean divided by sigma. X is 10. Mean is 10. Sigma is 4. I have 0 divided by 4. Remember that 0 divided by any number is equal to 0. So my Z-score is 0. Z-score is equal to 0. What's the interpretation? It means that this orange with rate of 10 is 0 standard deviation from the mean. It means that this orange is our typical orange. This orange is a typical orange.